Hi, Victor Morganta here from Fact Engine. Today I'd like to show you something that's coming to the Boston conceptual modeling software next week, and that's the ability to develop a property graph schema within Boston and automatically convert that to an object role model. For a long time now, you've been able to create your conceptual models in Boston using object role modeling and automatically convert that conceptual model to an entity relationship diagram or a property graph schema. The new release of Boston takes it one step further, where you actually can do your conceptual modeling as a property graph schema and convert that to an object role model or an entity relationship diagram. If you look at trends in the industry, graph databases have certainly made an impact over the last 10 years. It's also true that graph databases have reached the peak of the hype cycle and now on the decline. But if you look at the search volume data on relational databases, that has taken a significant hit over the last 10 years. Where we're heading into the future, though, is an amalgamation of graph databases and relational databases. We have at the moment a property graph schema working group working to implement features in graph databases that weren't previously there, that are akin to that used by relational databases. In the future, we'll see a merger of the two in what's becoming known as Relational Knowledge Graphs. So Boston and Fact Engine are perfectly poised to take you where you want to be with Relational Knowledge Graphs, where your conceptual model supports both property graph schemas and entity relationship diagrams and object role modeling to boot, and where your future database will support graph queries and SQL. So I hope you like the demonstration of where Boston is going. There's a lot more to talk about in the relational knowledge graph space, so please reach out to me at factengine.ai, and I hope to speak with you soon.
Hi, I'm Victor Morganta here from Fact Engine. Today we'll be looking at creating an object role model in the Boston conceptual modeling software, having first created a property graph schema. We've got Boston open in front of us, model open in the Model Explorer Cinema Bookings. We're going to create a model where people can book seats to watch films at a cinema. And some attribution: the original model for this demonstration was provided under the ActiveFacts GitHub page by data.constellation. Let's click on the model and add a new property graph schema page. And open that page. Let's open the toolbox and drag a node onto the page. Let's call this first node type Cinema. Now we'll provide a unique identifier for Cinema by giving it a reference mode, and we'll call that ID. So each cinema is uniquely identified by its ID. We'll also give Cinema a property, cinema name, so that we can identify a cinema by its name. We'll set that to text fixed length, mandatory, and 50 characters maximum length. And we'll set up a index for cinema name so that cinema can be uniquely identified by its cinema name as well. So we'll add an index to cinema. So we've got a new index called UC, which is unique, and we'll put that across cinema name. When I click on the primary index, you'll see that it includes the column name cinema ID. So the primary uniqueness constraint is across cinema ID, and we have a uniqueness constraint on cinema name. Let's apply that, and we can view the properties for cinema. So cinema ID and cinema name. In some graph databases, you never or rarely look at the unique identifier for a node at the data level, but at the schema level, we're indicating that each node at the data level does have a unique identifier, and in this case it's cinema ID. If we go back to the toolbox, we'll create a node type for film, and similarly we'll set up unique identifiers for film. So we'll go to the properties, give it a reference scheme of ID, we'll add a property film name. We'll set its data type to text fixed length, and we'll say 100 for film name. And similarly, we'll add a index for film name. So the primary uniqueness constraint is across film ID, and we're going to add a secondary uniqueness constraint for film name. Let's apply that. Now cinemas have rows of seats, so let's add a row node type, and we're going to create a compound reference scheme for rows, so we'll delay adding a uniqueness constraint or a primary uniqueness constraint on the row node type. We want to say that a row is in a cinema, and if we open the ORM reading editor, we can edit that edge type and change the predicate for the edge type to is in. So we're saying each row is in a cinema. Now we're going to add a row number property to row. And we're going to say it's, well, let's say it's an unsigned small integer. We're going to say it's mandatory. Hit OK on that. Now what we're going to do is add a primary uniqueness constraint, and we're going to put it across cinema ID and row number. This is because in our database we might have more than one cinema, so each row is uniquely identified by the cinema that the row is in, so a cinema ID and its row number. So we can talk of cinema 1, row number 1, or cinema 2, row number 1. We'll hit apply on that. Now let's create a seat node type. Similarly, we're going to give seat a property where each seat has a letter. I'm going to set that to text fixed length, mandatory of length 1. Hit OK on that. We're going to say a seat is in a row. Let's set the predicate for that, where we're saying seat is in row. And let's set up a unique index as the primary unique index for that node type, which is across cinema ID, row number and letter. So we can talk about cinema 1, row 1, letter A. So seat 1A in cinema 1. Let's apply that. Now the whole idea of the schema and the ultimate database is to book sessions. So let's create a node type called session, and where a session is for a film, and where a session is at a cinema. Now a session is also at a particular date time, so let's add date time as a property, and set the data type of that to date time. We'll say it's mandatory. And we'll set up a unique index as the primary unique index on that node type across cinema, film and date time. So you can watch a session which is a film that is showing at a cinema on a date time. So let's apply that. Now what we're going to do is convert this to a fact type. So at the object role model level it becomes a fact type. And when we click on session we can see that we can modify the reading for that fact type. So cinema is showing film at date time. So a session is where cinema is showing film at date time. Now of course we want people to make bookings. So we've created a person node type. We'll identify each person uniquely by their ID, and each person will have a person name property, and we'll say text fixed length. We're just going to have one field for person name rather than first name and last name, and we'll set the length to 100. So that's person. We'll set up a unique index for person name. So a person can be uniquely identified by their person ID as the primary uniqueness constraint or person name. Let's apply that. And in our database we want to store where person can like a film. So we'll set up an edge type, person likes film, and we're going to give that edge a property. Which is rating. So a person can like a film with a rating, so somebody can like the film Rocky with a rating of 10. We'll say that's mandatory for that edge type. And we've got an edge with a property on it there. So let's open the toolbox again. And ultimately we want to be able to store bookings. So a person can ring up the cinema and make a booking to watch a session, to watch a film at that cinema for a particular seat in a row in that cinema. So a booking is for a person, and a booking is for a session, and we'll set up a unique index where the booking is for a person and a cinema and a film and a date time. Let's apply that. Let's change bookings to booking singular. And for our purposes we're going to convert that to a fact type. And then we're going to say that a booking is for a seat. And of course a booking can be for many seats and a seat can have many bookings. So let's change this into a many-to-many relationship. And a person can like many films and a film can be liked by many people. So let's change that into a many-to-many relationship as well. So a person can like many films, a film can be liked by many people. The double arrow indicates it's a many-to-many relationship. So too with the relationship between booking and seat. A booking can have many seats and a seat can have many bookings. The two arrows is a many-to-many relationship. So let's convert this to an object role model. Our object role model is complete. We'll just tidy that up a little bit. So we've got sessions and bookings, and we're a many-to-many relationship between booking and seat and a seat and booking. We'll just show the fact type names on those. So we've got booking, session, and booking is for seat. Our relationship between person and film, where a person can like a film with a rating, and our object role model is complete. So we've seen how to create a property graph schema in Boston, and of course in Boston you can morph from the property graph schema to the object role model, and we've successfully converted our property graph schema to an object role model. Thanks for watching. See you in the next video.
Thank you for watching. I hope you enjoyed the video. I'm Victor Morgani from Fact Engine. Fact Engine provides consulting on knowledge graphs, object role modeling, property graph schemas, and relational models. And of course, Fact Engine is the author of the world-leading Boston conceptual modeling software. Thanks again. I look forward to speaking with you soon.